We continue with the second talk, given by Michel Broniatowski from the LPS in Paris, and he will talk now a different kind of flavor, so that really explains what Frank said. There's a wide variety of applications of divergences, and now there's another application, namely testing the nature and the number of components in a mixture.
Thank you very much, Wolfgang, for his very kind invitation to organize this. Okay, so the talk is on an old problem, actually still very active, on mixtures. Mixture structures have been considered decades ago, and the problem of homogeneity in a statistical population has been risen already for decades. This problem is still open, and this is an ongoing work actually, and we will have still very much work to do to have something quite complete on that. But the idea here will be to consider divergences as measurements from an empirical measure which is connected to the data with respect to a hypothetical structure that would be the mixture under the hypothesis that there is typically a given number of components, assessing that the distribution at hand may be coming from a global mixture. So we're looking at distances between models as such, a model and a submodel. And the contents will be first kind of general topic about what part of what exists in testing the number of natures of components of a mixture, and we will not assume that the components will be of the same nature. So not necessarily will we have to do with mixtures of Gaussian distributions. We can have log normal and variable or others. So we'll consider a setting, but this setting will still be in parametric models. We could also consider mixtures between parametric components and semi-parametric, typically, components. This has been considered elsewhere. This is a more complex situation than the strictly parametric one, but we will focus on parametrics as such. So I give you ideas on dual forms for divergences, because those are the forms under which we're able to handle a wide variety of situations, and including former kinds of forms like likelihood ratios and so forth. So we need some presentation on that. And then there will be something about the relation between the choice of the divergence and the problem at hand. Usually problems in statistics are considered stating, okay, we take the likelihood, or we take a chi-square or something, and we look at tests according to what can be said in a structure with such and such tool. But we do not focus usually on the adequacy between the tool and the structure we work on. And this will be considered in the role of divergence function assessing the nature. And then I will go to two kinds of situations, and I'll tell you it's ongoing. So there will be intermediate results. Okay. So let's first state a kind of notation. Here is a finite mixture. We'll keep on finite pictures. And the parameter will be both the weight and the parameters of each of the components. And the components will not need to be in the same family as such. We will need some identifiability conditions, which I do not state here, but we will assess that the problem is well posed somehow, although in the problems of mixtures, it is not such obvious, above all because we allow the weights to take values 0 or 1. And this amounts to say that the problem of identifiability is somehow complex as such. And so the parameter will be the family of the weight and of the parameters of each of the components. And the problem we have to consider is the number of null coefficients in the W's. So this is it. We will assume that theta 0 will be somehow the set of mixtures. Those are made by a subfamily of the former components, and we will assume that this holds, okay? So this is our way of writing globally the kind of situation. Okay, so we consider that we have the problem of considering if we have k non-null components and k0 and k minus k0 null components, and they are ordered in this way. So, okay. This seems a bit formal, and to say the truth, it is formal, because globally, as you will see, we will treat problems with k equal 2 and k0 equal 1. It works if we have many, many data for extended situations, but we do not have to figure that we can make something quite very impressive with few data. So basically, the situation at hand when we have 250 points is that we are not able to do mixtures with 5 or 6 components anyhow. Okay, so I just give a few outlook on that, on what is globally done in a very natural way. And the first natural way is to look at likelihood ratio, which is of this kind. But obviously, this works for what we would call regular situations. And regular situations means that if we look at the numerator and the denominator in this expression, the soup will not be at the frontier of the domains. Indeed, in order to find the limit distributions of such quantity, we need to make expansions. Obviously, this is Wilks' approach to testing. And this requires that all points around which we make Taylor expansions would be inner points in the domain of variations of the parameter. Now, the main problem with what we're doing is that testing for mixtures means that we intend to make derivation of those kinds of quantities at the border of the existence of the parameter, since one of the parameters maybe would equal to 0, and it would be a waste, and the waste lives between 0 and 1. So this has been the source of many difficulties, actually, in assessing the number and the nature in mixtures, because precisely of the fact that we are testing or estimating quantities, those are at the border of the domain, so this is not a regular situation. For example, here we consider a mixture with 2 known densities. We'll go back to this problem a bit later. And the test situation is written in here. And obviously, we consider the likelihood ratio, which is number 6 on this slide. And what can be seen, actually, this is an old result by Titterengton and others, but still before, is that the limit distribution of Wn, of the test statistics, is a bit awkward because it is a mixture of a regular distribution, which is a chi-square distribution, and a Dirac measure. And this makes quite a difficulty in calculating anyhow, and even in this very easy situation, the structure of the test. And above all, if P0 and P1 would not be known, and usually P0 and P1 are known to belong to some parametric families, but with unknown parameters. So this adds a state of complexity. Here is indeed a kind of overview, a very short overview of the various problems associated to this kind of situations, which are due to the fact that the test pertains to values at the border of the domain. There is also something to add, because we will use this later, is Shen's approach and Kalbfleisch's approach to this. And what they do is to somehow use a penalization factor in the likelihood ratio, and they can get to some distribution for this modified thing. Former results by Shen have also been produced, stating that he gets statistics for these kinds of problems, but the limit distribution of these statistics is obtained as the supremum of a Gaussian process, but the covariance, well, this is standardized, so centered and normalized Gaussian process, but the covariance structure of this process is somehow difficult, and above all, it does not allow for easy obtention of the distribution of the supremum of this process. So there are many results that do exist, but they are, I would say, rather complex in nature and hard to put in act as such. So what we will do, the idea here will be the following. We would like 0 not to be a border point of the domain. Now, if you look at a mixture with two components, let's take the one here, we could take theta between -1 and 1, for example, or -1 and 2, if you want. Obviously, this is not a family then of distributions as we consider them, but this is still a family of measures. And we have our data, so we have the empirical measure of our data, and ideally they come from some p theta t. Theta t would be the true parameter somehow, and we could project this on the family of all those signed measures, no more probability measures. This would be a well-defined object if the distance under which we project has some existence property between a probability measure and a set of signed measures. So this would be a statistics as such. We do not project on models that we would consider as probability models, but inside of them there is the trace that corresponds to theta equals 0. So we could just measure the distance in this sense. This is what we're about to do. So now we need to define the object for the projection. And well, there are many ways to define distances, and Frank just recalled us on Bregman divergences and extensions. Here I will just consider what they call F divergences, so Caesar type of divergences. And for various reasons, one of the reasons is that it's easy, and we obtain rather easily duality formulas for this. There are also other reasons which are stated here, and that state globally that would say, for example, total invariance. That means that if you make the same smooth transformation on Q and P, so this does not change the value of the distance. So it is intrinsic somehow. This is one of the reasons why we use that. This has been developed widely by so many people, Lisen Bajda. So examples. Here is a widely known family of such divergences. You see that all of those objects are defined through a function phi. And so you can look, and phi is convex and has some property. And it is quite customary by statisticians to consider classes of parametrized types of things. And this class, which is Crécy-Reed, is interesting because globally, but for the L1 distance, it contains globally what you want to do in statistics, basically. It's connected with so many other kinds of questions. Maybe we'll talk about this after. Okay, so globally, Kullback-Leibler, chi-square, modified chi-square, Hellinger, likelihood, etc. Are associated to that. If you take gamma equals 0, indeed you need to make an expansion for that, then you get to a generator which is minus, so phi 0, you see this is the likelihood distance actually. It induces the likelihood distance. between distributions, and as such, the likelihood ratio. Okay, now I will say 2 slides on duality forms for that, and I will just show them very simply in parametric models. This can be extended on measure spaces with other kinds of arguments, but it's a general frame for the study of distances between measures, at least in the context of Caesar type. So I start with the function phi and just write the fact that phi is regular and convex. So this is our first line. And then I put a notation and I take 2 points, which are those ones. So I restrict to parametric models. Theta t, somehow we would assume that this is the true value of the parameter. We'll think of it this way. And we have a parameter theta and alpha, and we define 2 points. And then I write the divergence, which is the distance, I'll call it distance, between p theta t and p theta. Okay, if I wanted to make optimization, I would take an infimum upon theta somewhere of this. Okay, but I take this quantity for theta fixed and theta t, which is assumed, and I look at this, so I plug this in, and I get this through integration with respect to p theta t. So this is just the first line integrated, and using a and b in here, no more. I take some analysis. There will be some condition. One condition will come after. You assume some integrability condition in such a way that I'm able to split the integral in 2 parts. And I see that this is always larger than that, but I see that in this we have equality when alpha is equal to theta t. That means that I can write that the phi is indeed the supremum of such quantities. And this means that we have what we would call variational form, or dual form indeed, of the distance between p theta and p theta t, which is obtained here quite easily through convexity integration. There are other forms of this in various contexts. This is a form, globally, if we extend this form in another setting, it turns to be, for example, for the Kullback library, what is well known in large deviation theory for the variational form of the Kullback, it's exactly the same kind of things. Resulting, okay. We will not need this exactly as such, but it is somehow interesting to see that because of the fact that the divergence between 2 distributions which are the same amounts to 0. So theta t is indeed the argument of the infimum, because this quantity takes value 0 in this case. And you see that this means that we have this equation, theta t, the true value of the parameter, can be obtained through this optimization problem as such. Now for a statistician, theta t is unknown. This is the true value of the parameter. We do not know it. But what we have at hand is obviously the sample. So what we know is that despite any statistician, Pn, which is the empirical measure of the data, will converge to p theta t anyhow. So we just plug in. You see that the interest of the formula is that it is linear with respect to the measure p theta t as such. We can plug it directly, the Pn instead of p theta t, and we will have convergence because of the law of large numbers, or uniform law of large numbers, of whatever. So we define in this way estimators of the true value of the parameter. And the interest of this approach is that if you think a statistician of a chi-square adjustment or these kinds of things, you remember that you have to make some grouping. And you remember that you need at least 5 points in a class to make test, chi-square, etc. There is no need for that in this approach, because you just have a plugin of distribution. So you do not need smoothing or plugging or grouping with that. Okay, so I just say now just one thing is that you see we had this quantity, and we can also somehow the problem for statistician is basically what happens if the data are not exactly under pt, under p theta t. So somehow we can manage, I will skip this slide, but we can manage for those problems of robustness, saying that anyhow, if ever x1, xm come from some p0, then anyhow the divergence between p0, which is then under misspecification, and p theta would take this form, where the soup is taken on a class that contains actually dp theta divided by dp0. And now what we know is that if we take fn, that would be an estimator of p0, say kernel estimator, then we will have anyhow some way to handle problems of robustness. So I will skip this precisely now. Okay, what is of interest for us is the test statistics for the number of components. Okay, so we turn to the distance between p theta t and p theta, and we have this formula. And so we're able to write down an estimator of the distance between p theta t, which we do not know, and any p theta. And now we turn back to the problem of the test. And test was that theta belonged to some theta 0, null hypothesis. Okay? And so we look at the distance between somehow p theta t, or pn, say, and the submodel. And this is the test statistics that we will be considering. First of all, a result. So you see that this is a global result. We will use it for mixtures, but it is a result of global results for parameters as such. And in the problem of mixtures, we have simply the fact that what we call the parameter in here for H0 is the fact that the number of those subparameters are equal to 0. So what we have, for example, so the basic point is this one. If theta t is in here, theta t here would be the truth under theta 0 typically, so it will be the border point. So this is why we need to extend the domain. So whenever theta t, for example, corresponds to one parameter, to one component, that means that theta t is equal to 0 because it corresponds to the fact that the weight of the other component is 0 as such. Then what we have is this limit statement, and this limit statement is exactly the same actually for the likelihood ratio as such. And so let's consider an example. We take now a mixture with two known components, and we insert this, we embed this in signed measures. So P0, P1 known densities. Mixture case theta t equals 0, which is the one we want to test somehow. This is H0 as such. In this case, is interior in the parameter set. We set, so in this way, the test takes this form, and we will see that this leads to, okay, so a few things on the bibliography on those kinds of things. And we will see afterwards in the example what comes out as the result of this theorem, of this convergence result in this setting, and about the power of such tests that we can obtain. Okay, there is here an important thing to be said, is the analytic properties. Those were necessary in order to obtain the duality formula. Basically, we needed some integration condition here. And what's important for this is there are two things. First of all, the divergence should be such that the domain of the function phi would also include negative numbers, because we want indeed to have those new models or kind of models. So what we have chosen is to take two examples. Chi-square divergence, so this can be extended on all R. And so this is a candidate for the choice of the divergence in order to assess the number of components. You cannot do that with Kullback-Leibler, strictly speaking, or with Hellinger, for the reason that the divergence is not defined properly at the border point. Or here is another example with Wolfgang. We've been able to extend number of divergences in such a way that the domain divergence functions include negative numbers. And so we have quite a range of tools. But you see that, first of all, the tools should be adapted in the sense that it should allow to obtain an interior point. And secondly, we have this integration condition. And what's interesting is this, is that according to the choice of the divergence, the condition under which we have this dual formula, and therefore the estimate, and therefore the test, is not equivalent at all. So for example, if we take the chi-square, we need conditions on the two components. If we take this kind of Kullback, extended Kullback, there are no conditions at all. So you see that this is also an issue, that we need to adapt the kind of tool to the kind of setting. Okay, here is the result, which here's a misprint, is theta times plus 1 minus theta here. Okay, and 0, 8 and 0, 2 are the points under which we take the power. Okay, but that means that we have here two components known. One is log normal, one is variable, and we want to test whether we have only a log normal component. So we test for theta equals 0 in this, and we have 250 observations, and we have taken, in order to assess the power, this counter hypothesis here. Okay, what comes out is that it's okay. I mean, the power is good. We have something which is okay with a regular asymptotic distribution for the test, which is the most important thing. Okay. So this is for known components. Known components and known weight. And two components, okay. Now, what we want to do is to know something what happens whenever the distributions are unknown. They are in known families, but we do not know the value of the parameter. So we have to estimate the value of the parameter and make the test. But the first thing is to set the problem decently. So we have a first family here, we have a second family here. We have some fact that they do not overlap somehow and so forth. But the important thing is to set the problem. We say that if ever for one choice of a distribution in F0 and one in F1, those are the two parametric families, we are able to state that there is heterogeneity with respect to only one component. This will be enough to say that we have found a submodel for which the data can be stated as heterogenic, and so we reject homogeneity. So this is what is stated here. And that means that we have this. H1 is whenever there exists a lambda 0 and some lambda 1 in this. And in this case, if ever we're able to reject H0 in favor of this for one and only one choice of this, then we reject the possibility of homogeneity. There should be a discussion about this, but it's okay. Okay.
Sorry, but I'm going to run out of time.
Oh, okay.
I have
so here are a few performances of this. And this can be compared with Chen's model, actually. And we see that globally, many problems are still quite open about the choice, about how to obtain critical regions for a given alpha and so forth. This is done by simulation. And there is much to say on that. Okay, so that means that here is a gamma mixture with unknown parameters. And but this can also Where are we? Is that? No, it's here, this way. Okay. And so here, log normal mixture, and it. I don't know what 28, okay, it's nearly over right now. Power for two component mixtures, and we also have it for mixtures of different types of distributions. Globally, it's something that seems to give at least performance. You may think that the power is rather low, but in those kinds of configurations where we estimate parameters and test, the power globally is low as such. Okay, so this is it. Thank you very much.